We're gonna get started.
Hello.
Hello. Welcome to another Papers We Love. Are we yes.
We're live?
We're live.
Are we streaming?
He said
streaming?
that we were streaming. Yes.
no.
Okay. All right, this is August. We have a full lineup for the rest of the year. We need 1 mini to finish the year. We'll do something special in December, right?
Yes.
Okay, good. So we've committed some budget to make December.
Yeah, it'll be great.
Be cool. Yes.
Announcements.
Yes, you do it.
Administrivia. We're doing a conference next month in St. Louis on September 28th before Strange Loop. So if you're going to Strange Loop, you should probably attend Papers We Love as well.
Tickets are very, very cheap. They're like, what, $40?
Yeah.
Yes. So if you're in St. Louis, just come a day earlier, and it would be really nice. Yeah.
Yeah. Bathrooms are at the back and to the left over there. Yeah.
If you want drinks, you have to have your wristband, and then there's a very nice bartender that will give you things.
Yeah.
That's okay. We have an announcement.
JD has an announcement to make.
Mostly I just wanted to come here to say thanks to Drew, who's in the back.
Woo, Drew.
Thank you, Drew. He's volunteering his evening, as is whoever's on bartending, though they probably won't be here for the whole evening. Also, we are GitHub, you know what we do, but just wanted to call out a few things. We are looking to talk to folks who want to work on understanding code, particularly the 400 terabytes of it that we got in about 300 different languages. And also folks working on distributed systems, distributed file systems, that distributed processing, data center management, Kubernetes, that type of stuff. What else? Also, we're hiring a CEO, if anyone's looking for it. So if you're interested in any of those things, you can come find me for the next 30 seconds, but I actually got to go bounce to put together a Burning Man van. So you can email me, jd@github.com, if any of the above sounds remotely interesting. But yeah, welcome to GitHub. Thank you. We're very proud to host Papers We Love. So
thanks. Woo.
It is so nice to be back at GitHub to host this meetup. They've always treated us so well and been so nice and generous, and it just feels super right to be back.
Okay. Do you have anything else?
Well, the last thing, and we've talked about this 3 times already, but we are streaming live at live-stream.github.com. So if you want to tweet it and have your friends watch the talk, you should do it now.
The Wi-Fi.
What's the Wi-Fi, Drew?
So, okay,
Octocat 11.
Yeah, and then there's going to be a thing that announces it. Okay,
great.
So if you're not familiar with our format, the way that we do it is we have 2 talks, a mini, and then Andrew's doing our mini, and then we have a full-length talk. We introduce both speakers, and we introduce them with their real bio, and then we make shit up as part of their bio. So let's introduce André. André Arko leads the Bundler and RubyGem teams. He co-authored the Ruby Way and blogs at arko.net. He works at Cloud City as a software development consultant and founded Ruby Together, a nonprofit that pays for work on Ruby open source. When he's not working on Bundler, André enjoys expanding his collection of taxidermied Persian cats. Let's give it up for André.
Hello. Hi, everyone. Cool. Well, let's get started. Hey, it's working. Awesome. So I'm André Arko. I had no idea anyone knew about that collection of taxidermied Persian cats. That's very embarrassing. Thank you, Inez. I'm indirect on the internet things, and I'm going to talk about Robinhood hashing. Bear with me, this is basically only one idea, but I have 5 or 10 minutes worth of backstory so that you'll understand why the idea matters. And if you already know how hash tables work, I'm sorry, this is not going to be super interesting. Depending on what programming language you use or where you learned about them, maybe they're associative arrays or dictionaries or hash tables or hash maps or hashes or something. Those are basically all the same thing. But they're one of the most common data structures used in programming, and that's for a pretty good reason, because they let you use almost anything to keep track of other things, which is really handy. So before we can get to the magic of Robin Hood hashing, I'm going to explain how hash data structures are generally implemented, and then we can be all on the same page for the exciting part. So how are hash tables implemented? Well, I don't know if you've ever actually looked into hash table implementations, but they're almost always an array. So the interesting part is that the hash is backed by an array that has numerical values, even though the things that you're using to index those values are non-numbers. So the way that hashing algorithms are backed by arrays is that you apply, the way that hash tables are backed by arrays is that you apply a hashing algorithm to the key, and it produces a number, and you use the number to know where in the array to store the data. The hashing algorithm is why it's called a hash table. So there you go. Now that you have an index value that's a number that you can use to store the data in an array, I guess the hashing algorithm itself is like an entire field of computer science that has all kinds of interesting things in it that I can't tell you about in 5 minutes. But for our purposes, we're just going to talk about the particular kind of hashing algorithms that are useful if you're working on a hash table. And hashing algorithms for hash tables are basically evaluated on a single criteria. Do they produce numbers that are distributed evenly and or randomly, especially when the inputs are not random? And the reason that in a hash table you want randomly distributed inputs is because the more evenly distributed the numbers that you get from the hashing algorithm are, the less there will be collisions when you're trying to insert items into the array that is holding all of your data. So here's what that ends up looking like. You have an array, like key on the left, number that the key hashed to, and then the actual array that's holding all of the data on the right. You insert values, this is cool, and then you have a collision. And this is a problem because the array doesn't actually have space to hold more than one value. And since the array doesn't have space to hold more than one value, you have to do something to be able to keep track of more than one thing, even though it hashed to the same number. So one of the solutions, and the one that was adopted by Java's hash table for most of its existence, for example, is called chaining. And basically, the array backing the hash table actually just stores a list of linked lists. And so chaining basically says, oh, everything that hashes to 4 is going to go into a linked list, the head of which lives at 4, and you have to iterate over the entire linked list every time you want to get something or add something or delete something if it hashes to 4. That honestly is still way faster than looking at an entire array. Like, it splits up your data into much tinier chunks, which is pretty great. But depending on your exact needs, it might not be very good, because linked lists mean that you have to go all over the place looking for other data when maybe what you were hoping for with your hash table was being able to immediately access the value. And so the Robin Hood hashing paper says chaining is cool and all, but I don't actually care about it. Let's talk about the other option, which is called open addressing. Open addressing doesn't use linked lists at all. Instead, it says we're just going to put the data in another slot in the array, and oh well. And so when you're using open addressing as the way that you calculate where to put stuff in your hash, there are a lot of different techniques that you can use to figure out what your second choice slot is, what your third choice slot is, etc. So for our purposes today, just because it's easy to demo on a single slide, I'm going to use maybe the stupidest possible way to pick a second choice slot, which is look at the next slot. So if all you do is look at the next slot, then you end up with something like this, where you're like, oh, well, 2 things hashed to 4, but 5 was empty, so I just put it in 5 and made a little note that, oh, by the way, you might need to keep going past 4 if you're looking for data here. And so most of the time, you only have to look in one slot, and occasionally when you hit some place where you've had to overflow, you'll have to check, maybe a couple additional slots. So as things continue and you have more data and you need a bigger array and more things conflict, oh, now we have something that shouldn't have caused an overflow except we previously had an overflow, so now it has to overflow into the next slot because we can still only store 1 item per slot. And I'm going to fast forward a little bit because we don't have that much time, but eventually what you end up with is something like this, where many things have ended up in many slots, and then an example of a worst case scenario happens, and you go, crap, where do I put this? Oh, well, actually all of these are full, so I'm going to have to put it all the way down here. And so this is an example of the way that open addressing in general causes a huge problem, because now if you have this array and you want to look up the last key, you have to start at slot 4 in the array, and then you have to iterate continuously forwards through the array until you find the thing that you actually wanted, which is now super far away from where you hoped it would be. And the closer the array is to full, the more pathological this behavior gets. And unfortunately, thanks to the birthday paradox, even with really small data sets, you end up with things that collide even if you have a lot less data than you think would cause collisions. And so this just gets really bad really fast. And so the terminology around how many times you have to look for something before you actually find the thing that you wanted is called probes. And using open addressing, even if you have a good hashing algorithm so that you have as few collisions as possible, and even if you do something clever, like say that your second second choice slot is actually a second hashing algorithm, so it's another set of things that are trying to avoid collisions. As the backing array gets more and more full, it very quickly escalates into a tons and tons of probes are required for every operation type situation. So this is where we talk about how Robinhood hashing is cool. It can be just hugely more efficient by stealing from the rich and giving to the poor, which is why it's called the Robinhood hashing algorithm. So in the context of a hash table, the rich are the items that are located very close to their actual index value in the backing array. The poor items are those that are located very far away from what their index, what their ideal index in the backing array would be. And that's the core technique of Robinhood hashing, which is when you're inserting an item, if as you probe forward, you find an item that is closer to its ideal than you are, you replace it, and then you continue the insertion operation using the item that you just replaced. So let's see. So first, the really great thing about this is that Robinhood hashing, in the end, offers you big O log n probes, where n is the number of items in the hash, which is just, if all that you, I guess, in 1986, this was kind of mind-blowing because no one thought that you could have a hash that was that efficient without doing pre-computation of keys or having additional memory to store calculations that some of the prior art discussed in the original paper is actually kind of amazing, like people generating binary search trees that they stored on the side to make it faster to look up keys when they weren't in their ideal locations and stuff like that. So Robin Hood hashing doesn't require any pre-calculation. It doesn't require any additional storage besides the backing array. And it offers this just like huge improvement in by reducing the number of probes that are required to find an item as you're looking at the backing array. So here's an example of what that ends up looking like using the exact same data that we just saw in that kind of like worst case type situation. So we insert all the things that don't conflict, or we insert the same data as before, and the numbers on the right-hand side are how far away the items are from their ideal location. And so here you can see that there was a hash collision in slot 4, and it overflowed into slot 5, and then there was a collision in slot 5, and it overflowed into slot 6. 6 overflowed into 7. 8 filled up, and now we have that same situation before that resulted in something being inserted 6 slots away from where it had started. So 0 is the same number as it would be for this item, so we don't swap. 1 is the same number as it would be if we inserted into slot 5, so we again don't swap. But on slot 6, 1 is lower than the number that the item we're currently trying to insert will have, which is 2. So we insert our new item into this place and mark it as 2 away, and then continue the search using the item that we just replaced. The item that we just replaced in the next slot will again be 2, and now we have another item to search. 1 and 2 will be closer, 0 is lower than 2, so we swap. 0 is lower than 1, so we swap, and then we're finally able to insert the last item with an offset of 1. And at this point, every single item in the entire array is 2 slots or less away, and so while it took us a tiny amount more effort to insert that item, now every future lookup of these items will be, again, big O log n of the number of items in the array. So that's Robin Hood hashing, and that's pretty much all I got. The paper itself goes into a lot more detail, talking about options for probing algorithms, options for collision, like second choice slot choosing algorithms, and techniques to try and make hashes that have had items deleted out of them faster. I posted, if you're interested in reading either the original paper, some follow-up papers, or a bunch of blog posts talking about different implementations and benchmarks and trade-offs in these things, I've posted the slides online at bit.ly indirect Robin Hood hashing, and you can check it out. There's lots more interesting stuff to be had that I couldn't talk about in 15 minutes. Thanks.
Any questions? Okay.
Yeah.
Coming to you.
One of your arguments that this was better than the things that came before is you didn't have to store this extra data structure off to the side, but it seems like you have to store the numbers for everything that's being hashed. Isn't that extra data stored in your structure?
Totally. So the problem with chaining is that you actually need an entire additional data structure per bucket, or you need a really big data structure that's full of multiple linked lists just kind of like piled on top of one another in a single array. And while this does require storing, I guess, 2 numbers per item, that's different in like type of additional storage needed from what was available in the literature at the time. I guess another example was like a technique that's discussed in the paper where you had an entire auxiliary binary search tree that you pre-computed as you inserted, and you needed that search tree to be able to find anything in a reasonable amount of time inside the backing array. And so in comparison, you don't need either a data structure per item or an entire gigantic data structure that's auxiliary. You just need some way to keep track of how rich each individual item is as you move along. I think over there.
So in 1986, preserving memory was really critical. It's not anymore. Is it worth re-examining those old algorithms?
So a reason that Robinhood hashing is actually super awesome today, and a reason why even that very quote unquote stupid algorithm of just putting overflowed items into the next slot is actually sometimes the most optimal strategy, is because memory buses are now usually the limiting bottleneck for algorithm runtime. And so even though we have lots of memory, the real question about whether you can do things quickly is if the data that you need is already in the cache line that you just loaded as you were looking for the item. And so getting things closer and closer to the ideal bucket dramatically increases the chances that the cache line that you loaded to look for the item will actually include the item. And so in many, I don't actually know how many, but like in some percentage of cases, I've seen people talking about how this exact approach of both the Robinhood algorithm for replacing items and using this just like very stupid algorithm of I'll just put it in the next slot was actually the most performant option even on a modern machine, because they didn't have to, for example, look up things in unrelated faraway memory before they could do the next calculation.
Okay.
Cool.
Thank you, André.
Yeah, absolutely.
I'm going to introduce our next speaker. His name is Scott. Scott Andreas is an engineer working on distributed systems and analytics. He focuses on designing large storage systems and compute infrastructure for batch and streaming analysis. Experimentation matters to him as he sees quantifying improvement through privacy-preserving analytics as one of the most important paths to building better products. In his spare time, Scott teaches small children how to do the Macarena. Let's give it up for Scott.
Can everybody hear me okay? Okay, cool. Ines, thank you very much. I made the mistake of sending that content to you from the presenter's notes of my first slide. So now my first slide is blown. I'm not seeing your slides. Yeah, can we cut over to... as Ines mentioned, experimentation matters a lot to me because I see quantifying improvement in analytics as one of the most important parts of building better products. I rehearsed this talk, but I received some pretty critical feedback last night that I've worked hard to address, so I hope you enjoy this. This talk is on a paper called Overlapping Experiment Infrastructure, More, Better, and Faster Experimentation by a group of folks at Google who presented at KDD in 2010. The focus of this paper is primarily on experimentation as a mantra and a native way of operating for engineers working in software development organizations. The goal is to be able to quantify improvement of each change made to a system as it goes out. So instead of thinking of it as like experimentation or A/B testing as an idea for trying something out, think of it more like the native way that you would go about shipping any change or commit or a PR to a system. In a past life, I worked for JD Maturin, who introduced us here at GitHub tonight. One thing JD was fond of saying was that every deploy changes a metric, and if it doesn't, either that deploy didn't do anything or there was no metric to capture it. So part of the concept here is having metrics to capture the changes that you're making to software. But how can you have hundreds, or in a large company, maybe thousands of engineers working on one product and running experiments on their components of that product at the same time, especially with limited traffic? It's likely that even receiving a very large number of hits or requests per second, that traffic space is still going to be limited relative to the number of developers you have working on the project. And what social processes do you need to have to make experimentation effective? I love that this paper draws attention to the social processes that you have to have in place for this to work well in the culture of a company. I think that the paper did a really nice job of drawing attention to those pieces. So This paper is going to cover the basics of traffic segmentation and diversion in online experiments. It introduces a concept of layers, which you could roughly map to services in your infrastructure. And it also has a concept of experiments that cross layers. There's a concept of a nesting structure that allows for complex arrangements and interdependence between services for experiments that need to have interaction effects with each other. It covers supporting analysis infrastructure, and it covers the social processes that you need to make experimentation work well. This talk might be a little unconventional for papers we love in that it's not like about some cool consensus algorithm or some rad distributed database, things that I love to geek out on. But it does cover the components of a functioning system from a high level that allow you to build infrastructure at a large organization to succeed. So zooming out a bit, let's talk for a minute about experimentation. So what do we think of when we think of experimentation as an idea? In the simplest case, you might think of trying something and seeing if it works. A more highly evolved form of that might be to say applying the scientific method, finding a purpose, doing some research, establishing a hypothesis, testing it with an experiment, and analyzing the results. In the tech world, it's common to hear experimentation referred to as A/B testing. We covered a bit on the social processes involved, like thinking of it more in terms of part of a release process. So in that sense, you could think of experimentation as part of RELEng or release management, depending on how you think about it. You could think of it as having a relationship to feature flags or possibly to software quality and quality improvement. So there are a lot of ways to think about experimentation as a concept. But what does the paper mean when it talks about experimentation infrastructure? The paper is referring to all of the supporting infrastructure and software systems that you need in place to make that a native way of developing software and products. So that means you need to cover traffic splitting and diversion, which covers who gets assigned or what requests get assigned to which experiments. You need to have the ability to implement an experiment in the app binary. So you've got to write the code that runs the test. You need to have the ability to apply runtime configuration changes to experiment parameters. It's unlikely that you'd want to hard code a specific shade of blue in an app binary, for example, and you might want to change multiple parameters or test different things. It's also likely that you have more sophisticated models or data bundles that might need to be deployed if you've learned something given a specific framework and want to apply that model at runtime. So there's probably some extra data that needs to be deployed. It presumes the existence of great logging infrastructure, which means the ability to capture the signal that your experiments generate, and the ability to analyze that data and to produce rapid reports and OLAP-style slicing and dicing to answer questions that you might have about the results that you get. So it's pretty simple to say A/B test, but the act of developing a culture of sophisticated experimentation and making that a way of approaching software development requires a whole lot of supporting infrastructure around it that can also make the software development process work a lot better too. So what's the scope of experimentation? Like, we might think of optimizing a marketing campaign or trying to get clicks through a funnel. You might think of changes to the UI or colors or email campaign subjects. But I would encourage a much broader view of the scope of experimentation. And I'd extend that to say that if you can measure it, anything can be the subject of an experiment. That could mean in your infrastructure GC settings, CDN configurations. If you're rolling out a new instance type from your cloud provider and want to determine if there is customer visible impact from testing it. New kernel versions, hopefully there's not a negative customer impact to a kernel change, but it'd be nice to be able to quantify that. The paper opens by describing the team's insatiable appetite for experimentation. And I think that's a really good way to think of quantifying change made to a system. It's not just shipping a PR and then hoping alerts don't go up in production. It's quantifying the business impact of every single thing that you do or the product impact of every single thing that you do. Though it's beyond the scope of the paper itself, it also presumes the existence of great metrics to evaluate the results of these experiments. So it's important to define what success means for your software, for your product, your customers, and your business. Pulling these things together help to align value from software development to customer to the business. It's a great way of tying that all together. So it's not just modifications to a user interface. It's more subtle changes. It could be learning algorithms for ranking or content selection. There's so much more that we can think of instead of surface level changes to the infrastructure. Before we dive into the meat of the paper, there are a couple concepts that we need to lay down that are helpful for thinking about the rest. The first is the concept of a control. The control is the opposite of a treatment. In the context of an experiment, it means doing nothing. So you're just testing the base experience versus the base experience. And that's called an AA test. It's similar in concept to a holdout group. which is a group that's not exposed to treatment once a treatment is in production. So the main concept is measuring the differences between a randomly divided population to help establish the noise floor of your experiment to make sure you know what noise looks like instead of testing something and thinking you've achieved a significant result when you're actually just measuring noise. The paper also introduces a concept called a domain. A domain refers to a diversion of traffic, such as splitting the total request space into segments of 0.1%. So if you want to do things like establish an experiment that takes 5% of traffic, you would be establishing a diversion of traffic to 5% of that domain. One of the central ideas of this paper is that traffic is a scarce resource. It's something that has to be conserved. You can only run so many experiments at once with a naive configuration. So if you have buckets of 0.1%, you could only allocate up to, say, 900 experiments and 100 control buckets, as an example. The central focus of this paper is how to get the most signal out of the traffic you have and how to empower many teams to experiment on the same traffic at once. In most organizations, you would expect that the number of people experimenting is proportional to the amount of available traffic. So ideally, the size of the organization is scaling with the amount of traffic that's coming in. Hopefully that holds true, but if not, this paper is also here to help you. It's awesome that André gave a talk on hash functions just before this, because hash functions are among the most important parts of diversion functions. In the context of diversion, one simple way of applying a diversion of traffic would be to take the hash of a diversion key and then mod it by the number that you would want to divide up into buckets. So if we were to create segments of 0.1% as described in the paper, you could take the hash of any diversion key that you want, mod it by 1,000, and then that will map that to a range between 0 or 1 and 1,000. So the main question of diversion is how traffic is divided among experiments. The concept is a deterministic projection of an infinite space, that's all your customers, all your traffic, into a bounded space, that range between 0 and 1,000. And the goal is to arrive at a uniform and deterministic random allocation of traffic. The paper introduces a whole bunch of different diversion strategies. One is completely random. So if you have queries or traffic that can be allocated on a totally random basis, you can do that. It describes a cookie mod strategy, which is a way of saying a customer should receive a consistent experience every time they use the product. So that means that if you were to hash on the cookie mod by 1,000, that means the same customer would always be part of the same experiment and get a consistent experience. The paper also describes a cookie day mod strategy, which means that you would get a consistent experience within a given day, though you might get a different one the next day. You could use a user ID, a session identifier, anything. But the base context there is that diversion is a concept that allows you to divert traffic into separate segments, and you can create different experiences for your customers depending on what's required of that given experiment. So by hashing that traffic into a range between 0 and 1,000, you could allow for, say, 4 different treatments at left, and then a control at right that you'd be comparing that traffic to. That's kind of the concept of a diversion in a single layer piece of a single layered experiment infrastructure. Let's talk about layers now. The paper defines layers as a subset of system parameters. So what is it that makes up a system that you would deploy? There's your app binary. Your app might have data that it reads from or that it serves up to customers. Your app probably has assets. It probably has style sheets. It probably has configuration that's associated. So there can be a whole bunch of different layers. You could also include every service in your architecture as a separate layer. So if we stack these up, we've got a few different examples of different teams who might work on different things. You might have the one team working on the app. You might have another team working on the data, and another team working on something else. Part of the idea in the paper is that there's usually interdependence or separation between teams who are working on these separate elements of the infrastructure. They're usually things that are independent that you can experiment on separately, like GC settings and background colors that probably don't interact. So separating these layers is key to conserving traffic and empowering large teams to experiment on a system together using separate segments of traffic. So if we think of layers like services, that's probably a simple way of collapsing the problem before we continue into something a little more complex. So what does it mean to have a layered experiment? The paper gives us this horizontal scheme for diversion, the range between 0 and 1,000, and this vertical scheme for layering, which are the separate applications. What the paper does next is to combine them. So again, if you remember nothing else from the talk, keep in mind that the central insight of this paper is the conservation of traffic for experimentation across large systems. let's take a single layer, but here we've drawn it as a larger 2D box instead of just a flat line. So we could assume that we're experimenting on a UI in this example. The range 0 to 1,000 represents our domains of traffic. That's diversions of 0.1%. To assign several different treatments to this domain, we'd bucket them in that range, like we did before. We've got our treatments at left, and then the control at right, covering our domains. So let's make this a little more complicated now. We were looking at just the UI layer here, but now let's introduce the concept of experimentation in a multi-layered system. We've got the UI layer, written by the UI team, a search results layer, managed by the search team, and an ad results layer, managed by the ad teams. These are separate groups. They're all probably pretty big, and they all probably want to be able to make changes at once. And each of these things come together to produce a functioning web page. You would have search results for a web page, maybe ad results off to the right, and then the UI that composites these together as an example. In this example, the layers are treated as independent and can be experimented on separately. That means different teams can perform different experiments on the same traffic. The search team might be performing experiments on indexing and retrieval. The ad team might be optimizing personalization for a particular ad category. The UI team might be testing variations of a background color or changes to a layout to see how customers interact with it. So we've got a concept of separation in this experiment using layers. Throughout the rest of the slides, I'll put the diagram used in the paper itself, like figure 2 there, up at the top right. I've vectorized them to make it a little easier to see here. But hopefully that'll be helpful if you go back to look at the paper and try to recall what we're speaking of. So let's revisit diversion to see how it interacts with layering. We've got our experiment space from 0 to 1,000 there. We've got, let's say, a few different treatments or a few different experiments that are happening across each of those layers. An incoming request. That goes into our hash function to divert that traffic to a specific segment. And the idea here is that each request is going to pass through a vertical slice of those layers. And whatever experiments defined in the layers that exist that it happens to pass through are what that request will be treated with. So in this case, that experiment would pass through the experiments defined for bucket 250 in the UI layer, whatever gets 250 in the search results layer, and whatever gets 250 in the ad results layer to produce a composed response that finally gets returned to the user. So we pass through those separate layers where each team is empowered to experiment separately to compose a response to the user and then log what had happened in each of those layers as part of the experiment. So this is how we might have 3 different teams who are experimenting on the same traffic in a layered system. But the paper takes it a little bit further. What we're going to introduce next is a concept of overlapping experiments. So the concept of overlapping experiments allows different experiments to be executed at every layer with n independent experiments on the same traffic at the same time to let large teams work together. But we don't have to just stick to flat, stacked layers. We can do something more complex than that. There are probably cases in your experimentation when you might want to have interdependence between these systems. The example that the paper uses is the case of varying the text color, like let's say making the text color blue, and varying the background color, where another team might want to make the background color blue. It would be invalid for a page to be rendered with a blue text color and a blue background color, which means that there needs to be a tie between those 2 different layers for them to experiment together and enforce that invariant. So what the paper does is introduce a concept of non-overlapping domains at left, which is a way of cross-cutting a whole segment of traffic to say, we're going to assign all of this to the same treatment together to prevent interaction effects from different experiments from occurring. So non-overlapping domains force cooperation across layers to generate valid results. The negative of this is that you lose that whole slice of traffic for experimentation in each of the individual services, but it allows you to create pretty sophisticated experiences that allow for experiments that aren't going to interact negatively or that can have some assertion for the results that they generate. It can get still more complicated. So the paper also introduces the concept of launch layers, which sit at the top. You could think of launch layers as the gateway for successful experiments to production. They're kind of like feature flags. So the idea is that if you have finished testing an experiment and decided that the results were positive enough to be pushed to production, you can promote that experiment from the current layer to the launch layer, which means that 100% of traffic is exposed to it. And then you freed up the space that you were previously experimenting in for different experiments to run. And all of that can be done through configuration changes in a system like this, instead of having to make changes to the app binary, deploy a new app, deploy a new config, and so on. So it's a great way of qualifying and moving changes through that release process faster without having to make a series of separate code changes. It's kind of like a feature flag. Of course, in a later release, you'd probably go back and remove the experiment code around that, so you don't have a whole bunch of ifs or other experiments implemented in the framework. But that's kind of the basic idea of launch layers, getting qualified code to production more quickly. It gets even still more complicated. So since this is a 2D space that has horizontal and vertical layers, we can do about anything we want, like add a carve-out. In this more sophisticated example, we have dependencies at left between the search layer and the add layer. And then we have one between the search UI layer with add results independent from it. And then the UI layer and the search results layer off to the right, which are independent from those. It's pretty clear that if you were to try to manage a system like this via manual configuration editing, or someone tweaking JSON or YAML, that it would get way too complex. The point of this is that it's important to have a system that composes these layers and domains for you. Because if you have 1,000 engineers who are working together on a system, there's no possible way that anyone could even conceive of the state of the system at any given time. But having a framework and library that enforces that and allows that and can plan that in a way that respects those invariants allows you to build a large system that allows people to experiment together safely on. One example of a really good planning tool that we'll cover in a little bit is Plan Out from Facebook, which was implemented a few years ago, partly in response to this paper, and makes a lot of references to the terminology that's used in this paper as well. Right, and then there's the same diversion of that traffic passing through and then hitting the launch layer 1, 2, and then the experiments at the left in the search layer and add layer. So the central concept there is taking what was previously a one-dimensional space, that line, and mapping it into a more two-dimensional space that allows you to do a lot more complex configurations of experiments and dependencies. So in that sense, like the story in Flatland, it's a story of becoming aware of a higher level of dimensionality and figuring out what it means to live in that world. So I wouldn't let the concept of nested layers become too complex, but I'd think of it as moving from a 1D to a 2D space for experimentation, and thinking of how that can be used to divide up traffic. So that's the core of the overlapping experiment infrastructure component of this paper. The paper introduces quite a few more concepts, though, that help you further conserve traffic. So if the paper's central theme is how to conserve traffic for experimentation in large teams, this is sort of the piece de resistance of it, but it also introduces several other pieces that can help too. One of those are conditions and predicates. So conditions and predicates allow for conservation of traffic and evaluation of signal because you know a priori that some experiments won't alter all traffic. The example that the paper gives is experiments that affect only traffic in Japan have no need to be exposed to traffic that's in North America. So if you can tell a priori that it's impossible for an experiment to possibly alter the results, there's no need to give up that traffic to an experiment that couldn't possibly be impacted. So this both saves the allocation of that traffic for other experiments, but it also reduces the noise from traffic that could not have been impacted because you're not analyzing something that is just pure noise anymore. Some of the examples that the paper gives for that are countries, data centers, languages, browsers, operating systems, whatever your experiments touch. Like as the author of an experiment, you know what it's going to impact. Well, you may know what it's going to impact, and you may be able to assert that some things won't be impacted. So for the things that you can prove positive no aren't going to be impacted by preconditions in your code, conditions and predicates are a great way to restrict the allocation of traffic to only things that'll matter. There is an even more powerful way of evaluating this, though. I had to read this section of the paper probably 4 times for me to understand, and then dig quite a bit deeper for it to actually make sense to me. So I would encourage you to read this section a few times, but this is one small portion of the paper that provides one of the single greatest contributions to signal and evaluation. The concept of counterfactual refers to what didn't happen. So the question is, given a request that falls into an experiment, what would have happened if that request weren't in the experiment? What would have gone to the user instead? Implementing that would require executing both branches of the code or doubly executing the request. So there's a latency and performance hit, and there's also analysis overhead for combining the counterfactual result with the factual result of what went into the experiment. But it allows you to compare the experience that the user got to the one that they would have had. And if those two things are equal, then you can throw that out as noise too, and not analyze it and have it pollute your signal. But even further, the more interesting thing you can do is to compare the two results that come back from the factual request that you return to the user and the counterfactual. Because there might be some things that you can assert without having user feedback about the quality of those results. In the example of an ad ranking system, you might have an experiment that returns an ad that has a higher cost and is more likely to be clicked by the user, and then a base experience that might fall back to a house ad because it's unable to place. So if you can evaluate that ahead of time and say offline, look, I know we don't want to return a house ad, then that's a great way of saying the experimental result was probably better, even if I don't know what would have happened otherwise. So it makes it possible to do additional comparisons between the output and the supposed quality based on known characteristics of the result set. By doing this, you can gain tremendous increases in statistical power and conservation of your request volume. Again, read this paper, or read this section of the paper several times. It's a really good section to cover. But why make all of this so complicated? The biggest reason to make it complicated is to cover conservation of traffic and to make use of this scarce resource across large teams of engineers. It allows for interdependence between layers, being able to implement experiments that could conflict with each other and preventing that from happening so you don't serve a blue page with a blue background. The ability to add launch layers, so you get feature flags for free in this system. It gives you a safe mechanism for promoting tests to production, which makes experimentation easier to swallow as a native way of operating. Developers get to ship their code faster, and they get to see their changes in production faster, and they get to quantify the impact of every single change they're making on the ultimate customer experience. It lets you release better quantified results to customers faster. But in terms of complexity, there's also software like PlanOut that can do most of these pieces for you, reducing that complexity. Because if we had to keep all of this in our heads, there's no way we could do it. The cognitive load is far too high. So this is some of the reasons why this infrastructure gets a little bit sophisticated. There are a few additional concepts that I wanted to cover. Statistical power calculation, pre and post periods, learned effects, AA tests and measuring noise, and then my last, which is also a favorite, interleaved result sets. On statistical power calculation, I'm not going to go super deep in here. The paper covers this math in detail, but you could think of statistical power calculation as a function of how much traffic you're willing to spend, the size of the effect that you want to measure, and the amount of time that you have to run that experiment. Time and traffic are kind of the same thing in that regard, but traffic can also happen while you're asleep. The paper contains the math and the details, but the point is that this should be incorporated into the planning tool. So as developers are planning experiments, they can understand if they're making a change, how much traffic is likely to be impacted, which helps them quantify their impact on the business at the earliest stage, but also helps them understand how long that test might take to run to get to significance. Pre and post periods are also pretty important. You could think of these like running an AA test at the beginning of the experiment and at the end of the experiment on the same slice of traffic. What this can help you do is to ensure that the diverted traffic that you're using in the experiment is comparable to the control traffic. The big idea there is making sure that your traffic isn't full of robots and synthetic traffic. Even if we have the greatest hash function in the world, if a robot happens to hash into a same bucket and blows out the traffic volume, then that could pollute our experiment space super easily. So comparing those controls with an AA at the beginning and the end using a pre and post period is a super great way to identify any of that traffic and then filter it out or go through a scramble to figure out where it's coming from. Pre and post periods also kind of lead us into learned effects. The big concept with both of those is that the experiment doesn't end when you have ended the experiment, because people have been exposed to this, and if you're introducing, say, a new behavior, customers will learn things about that, whether or not they cognitively learn it at a conscious level or not. The idea is that if you move a button to a new place, people will learn to look for it and click there. If you make it possible to perform a new type of query, you'll find customers using it. If you fix a bug, some people will notice that bug is fixed and then begin relying on that new behavior. So the point is that experimentation doesn't end at the conclusion of the experiment, because that'll impact future behavior too. So if customers have been exposed to some behavior and then they get hashed into some new experiment, it's quite likely that that behavior from that previous experiment might also be a carryover effect into a new one. So rehashing across buckets is a decent way to separate that space again and then divide those users that have been assigned to previous experiments back across that random population. AA experiments and measuring noise. So again, the simple case here is understanding the noise floor of your traffic, given the volume that you have. The more complex cases are bots, synthetic traffic, test traffic landing in particular buckets and polluting your experiment traffic. So also, all good things to eliminate and make sure that you can filter out from your analysis. There's one last cool one that I wanted to cover, which is called interleaving. If you Google balanced interleaving, it'll pop up a separate paper on this topic. But the idea is that if you have a system that returns sets of results, so that could be ad results or search results in the context of the paper, and you want to know which of those two sets is best, in the simplest case, you could serve one set to some group of customers and another set to the other group of customers. What interleaving does is it would say, given these two sets, let's pick one from A, one from B, one from A, one from B, and then keep track of which set those results came from. And if customers happen to click on those from result set A or result set B more, you can determine that those results should be either ranked higher or that ranking algorithm might be superior. It's also a way of reducing the risk because you're exposing two sets of results, say a known set and a test set, to the customers, and you'll have the highest rank from the known set, at least in the top 5 or so of that ranked set that's merged. So interleaving is also a pretty cool but also fairly advanced approach that can be useful if you serve information retrieval systems or systems like ads. So after that, the paper also covers more things like infrastructure that you need for analysis. It's kind of funny that the paper dives into some of these things, but the paper says you need to have fast analytics, and you need to have a good user interface, and you need to have a good experimenter experience. These aren't really things that you would normally say in an academic paper, but it's super true. Like if you're driving after a great developer experience, you need to be able to ask questions fast. People ask more questions and they understand more if they can click buttons and get answers quickly instead of entering a query and then waiting 10 minutes for a result. Like you're simply going to ask more and learn more if it's a matter of interactive latency. The paper says that you need multidimensional analysis tools where you define everything as either a dimension or a metric, which you can then feed into in-memory OLAP systems like Druid. You need standardized metrics for evaluations. So one of the things that the paper points out is that everybody shouldn't be defining their own metric. Organizations should be aligned on what's important to them and what the goals are for a system. Doing that means that the organization knows what the organization wants. It also means that you have a stock set of metrics that every experiment can get for free to see whether they move them up or down. Notwithstanding the point on standardized metrics, the paper also says, also you should be able to define custom metrics. So to that point earlier about having things that you might change that wouldn't have a metric associated, it should be possible to define a custom one for a test to be able to evaluate if there's one that's specific to your experiment. But yeah, the point under this infrastructure for analysis section of the paper is that questions that are asked are a function of the time that it takes to ask them. And if you can ask more questions more rapidly, you're going to learn a lot more from the results. If you've gone through all the effort of implementing experiments and the infrastructure to do this, but you can't ask much or learn much from the analysis, all of that's wasted. So much effort here is very important. The social process was probably my favorite part of this paper toward the end. It's geared toward helping people design good experiments and to get good at that process. The paper describes defining an experiment council. So this is a group of people who are responsible for helping people create good online experiments. It describes having a web-based tool that helps people plan experiments and schedule them over shared traffic. It also forces you to think about a lot of interesting questions like the characterization of the experiment, its setup, the diversion and triggering, the analysis and metrics that people plan to perform, the sizing and duration of the experiment, and the experiment design around what's being tested. It might sound kind of like a pain to fill out a form to answer all those questions, but the act of thinking through all of these things in advance is actually super important in software development, let alone experimentation. So it's a good process that is designed for people to be able to move through pretty quickly and to guide toward software development and building better products. It's not meant to be burdensome in that regard. The concept of an experiment council or having a social process here is also an opportunity to set standards for ethics in software development and provide an opportunity for conversations and review if there's ever question about this. We've all probably seen stories of ethical quandaries in software engineering over the past several years, so having a formal process for discussing these things and reviewing them together is a really good opportunity for people to come together and say, well, wait, that's actually kind of concerning what that could do. We should talk about that. Having that as part of the process is super important. Another point is that it's not just experimentation, it's software development. So that's not something that should be applied to just say like, oh, we're only going to touch 1% of traffic. Like if the idea is to promote it to 100%, that ethical conversation should take place across the entire spectrum of the traffic as if it's a production deploy. And then finally, that social process also becomes part of the deploy and release engineering process too. It's not how you run an experiment on traffic, it's how you get code to production by rolling it out incrementally and then launching it once the results look good. Those are kind of the fundamentals that the paper describes around that. In terms of further reading, there's some super great stuff, but I think my favorite is a paper called Designing and Deploying Online Field Experiments from a couple folks at Facebook that was published in 2014. Not only did Facebook just write a paper, they did one better and released an implementation. So if you go to facebook.github.io/planout, you can download their Python tool for planning that sophisticated overlapping experiment infrastructure that we defined back here. So instead of this being something that is super complex and maintained, it can actually be some nice testable Python that generates configuration for systems for that can also be tested as well. So there's a lot of good infrastructure that's been built in light of this paper and that even references the specific terminology of this paper, if you take a look at that. There's also a nice link that I'd recommend taking a look at that covers horrible things that can happen, pitfalls to avoid when running controlled experiments on the web. This helps you avoid possible mistakes or possible misinterpretations of the results that you might see. But the footnotes for this paper and the footnotes for the Facebook paper are fantastic. I'd encourage you to check those out. That's what I had. We kind of blew through quite a bit pretty quickly, so I'm happy to stick around for any questions you have or discussion on things like counterfactual, experimentation, software development. Thanks.
Kevin.
Thanks, that was a really great talk. So you mentioned that building out experiments requires a whole lot of supporting infrastructure. Can you talk through some of the social processes and what you had to do to sort of roll this out at your company or your experience dealing with that?
Sure, yeah. I think the plan out case is probably a good way of thinking about that workflow. So in plan out, you're writing a bit of Python to define your experiment, and that Python can be submitted as a PR. Those are items that could be submitted as part of a template in a PR. Or as part of a discussion. So that's probably the simplest case. The paper itself just says a web form, which could mean a Google form or a Google survey as part of creating an experiment and registering it in an application that plans them. The point is to make it not burdensome, but also help people understand how to define good experiments that ship their software. So I think the bar should be closer to what you would need to do to get a PR out than some complex experimental design, psych grad study type thing.
More questions.
Thanks. I just had one quick question. Great talk. So with the conditions and predicate stuff, you apply that before the hashing or after? Do you hash it, look, say, oh, this doesn't meet it, or do you basically segment the whole traffic stream into the Japanese traffic stream and then hash?
Yeah, that's one of the biggest questions that I had about this paper. The paper speaks of it more in context of traffic selection, which sounds like there could be a more complex process than just a straight hash function. So I think that there might be something more complex that's implemented but not described in that paper itself on how you can select or filter out traffic while also obeying those properties of random assignment and consistent assignment. I'm not actually sure on the details of that one, but that's a great question.
How do you determine interaction for those before you lay out your variants there?
Yeah, there are two ways. One is it might be possible that you can assert that. And if it's not possible that you can assert that, you can also test both. So you could have two separate configurations, one that tests them independently of each other and the other that varies them together. You have to give up a bit of traffic to do that, but it's a good way of understanding if there is interaction between those two things.
And also the non-overlapping?
Uh-huh.
Is that just things that have one treatment in the whole stack?
Oh, yeah, exactly. So if it's non-overlapping, then this is sort of like that base case where you just have a one-dimensional.
I think my question might be similar to his first question, but it seems like a lower layer you might have be testing something different in the same domain and that might influence the results of the UI layer. Do they talk about like how to avoid that or how to detect when that happens?
I don't think there's a very deep discussion of that case in the paper. I think that testing both is probably one good, quick way to try that out. The other way is by rehashing or separating those and running the experiment again, such that those are separated from each other. That was a little further in here.
Any more questions? Oh.
I want to ask again, sorry. So a lot of organizations, like you build a feature and then you roll it out and then you kind of move on. How do you switch from that to, do you have any experience, how do you switch from that to an organization where like you build a feature and then you experiment on it and you kind of implement the things in the paper, right? Or even get to the point where you're implementing the things in the paper?
Sure, yeah. I think of that more in the context of the changes that you make to the product and finding ways to measure those changes than a whole lot of experimenting in the context of like experimenting with changes in the product. Like in that sense, most features aren't just sort of left, they're maintained or changes are made to them. So as you make those changes, figuring out how to measure those incremental changes.
Here.
Sometimes we don't change anything, but the metrics still change. And right, how do you fit into any kind of framework?
Sure, no, that's a great question. Do you have an example of a null change that led to a change?
I was trying to run my own startup in India, so we're just selling cars. And in certain months we were selling more cars, and certain months we're not selling more cars. Obviously, I don't know why. That's why I had to shut it down. But but there was still variation in what we managed to perform.
Totally, that's a great point. So in terms of the time component, there's always huge seasonality effects in many different types of traffic. So comparing the same traffic in January to what seems like the same traffic in March or June could be very different because the behavior of people is very different. Part of the idea is that you'd be comparing on a per request basis at the same time. At the same time also, if you're measuring differences in that AA, then that is sort of defining what that noise looks like and helping you understand what that noise floor is for that traffic.
There's a bunch going on about dividing up the traffic that you have and conserving that traffic. Is it possible to drive this backwards and say, I have this many experiments I want to run, I need this amount of traffic? Like that doesn't work for the, Google is trying to test their base, but if you are trying to do performance testing on a bunch of different new features, you might want to know, how much infrastructure you need to test that in a reasonable amount of time.
I think that's kind of driving the same statistical power calculation function in the other way, so solving for the other variable. That's defined in the paper, so if you wanted to plug that in and run that the other way to see how much traffic you would need to be able to measure an effect of a specific size, you can answer that.
Cool.
Anyone else? Anyone?
Eh?
No?
Okay.
You, one more.
Do you really use just one number line, or do you have multiples?
One number line or so in the context of the paper, the idea is that every request is traveling vertically through those slices and through those layers. Possibly in the context of the question that Jordan had asked about how you would allocate traffic with predicates, you could have a more sophisticated traffic allocation function. So it's probably possible to define a system like that. That would be distinct from the system that's described in this paper.
I have one. So you worked at a lot of places, right? At which size of a company do you get to have the discipline enough and also enough teams that are trying to push it out where this becomes a thing that you reach out for?
Sure. I feel like that would probably be in the maybe 50 plus or 150 plus range. It might be smaller with a much smaller team, in the 30 range or so. But with new tools like PlanOut that make it easier to implement experiments like this, and with cloud-based tools like BigQuery and Redshift that make it easy to store and index data, the overhead of maintaining that infrastructure as a small team is a lot lower than it was several years ago. So I think that you could probably implement something successfully with a smaller team, and then also have a pretty good sense of the impact that changes are making on customers as a result.
Okay, one more. Okay, how much traffic? is the question.
It depends. I mean, I guess that comes to the statistical power calculation question. There's also the question of the value of that traffic to you and the value of making changes to that traffic to you. I don't feel like it'd be appropriate to offer like a request per second or like number of unique users type number. But so long as you can measure the magnitude of the effect that you hope to measure in making a change, then I'd say that you have enough. That might be super unsatisfying, but I'm going to be hanging around after too, so feel free to come hang out.
All right. Thank you so much, Scott.
Thank you.
Thank you.